Combined electromagnetic fields and Lorentz force. Combined electromagnetic fields means if in a region there exists both electric field and magnetic field, it is known as combined electromagnetic fields. We know in an electric field, a charged particle experiences an electric force given by the equation vector Fe equal to Q into vector E. In a magnetic field, a charged particle experiences a magnetic force given by the equation vector Fb equal to Q into vector V cross vector B. So, in a combined field, it will experience the sum of these two forces and the total force is known as Lorentz force. So, Lorentz force is given as vector F equal to vector Fe plus vector Fb, that is Q into vector E plus Q into vector V cross vector B. If the both electric field and magnetic field are perpendicular to each other, it is known as a crossed field. That is, in a crossed field, electric field and magnetic field will be perpendicular to each other. Let us see the applications of crossed fields. First one is velocity selector and the second one is cyclotron. Then first application is velocity selector. Velocity selector is used to select charged particles of a particular velocity out of a beam containing charges moving with different speeds. That is, if we have a beam containing large number of particles moving with different speeds, and if we want to pick up only one particle having a specified speed, we can use velocity selector. Consider a charged particle having charge q and moving with a velocity v in a closed field. So let us see the condition for the velocity selector. For that, consider a closed field and suppose a charged particle is there. It is moving with a velocity v and it is having a charge q. The different directions are as shown here. That is, the direction of velocity is along x-axis. The particle is moving along x-axis. Therefore, the velocity we can write vector v equal to vi cap. The direction of electric field is along y-axis. That is vector E equal to ej cap. I cap and j cap all are unit vectors used to denote the directions. I cap to denote x direction, j cap to denote y direction, and the direction of magnetic field is along z axis. That is vector b equal to b k cap. K cap denotes z direction. Here this v, e and b all are magnitudes only, and this unit vectors gives the directions. This is the directions are represented diagrammatically. You can see velocity along x-axis, electric field along y-axis and magnetic field along z-axis. So since the particle is in a combined field, it will experience Lorentz force given by the equation sum of electric force and magnetic force, that is Fe plus Fb. So we can write vector F total force, vector F is equal to vector Fe plus vector Fb. What is vector Fe? That is Q into vector E. Plus what is vector Fb? That is Q into vector V cross vector B. Now let us see each term separately. First let us see the electric force. That is vector Fe equal to Q into vector E. What is vector E? That is ej cap. Therefore we can write QE j cap. Similarly, what is magnetic force? Vector Fb. How we can write vector Fb? Q into vector V cross vector B. From this first equation, here we got electric force. And from this equation, it is clear that the magnitude of electric force is QE and its direction is given by J cap. J cap denotes positive y direction. Therefore, the direction of electric force is along positive y direction. Similarly, from this equation, let us find out the magnitude and direction of magnetic force. To find the direction of magnetic force, either we can use right hand rule or we can directly find the direction from the equation itself. So let us find the direction from the equation itself. So let us rewrite the equation. Vector FB equal to Q is there, Q into what is vector V? Vector V is VI cap. So put there VI cap cross what is vector B? That is BK cap. For BK cap, where this V and this B all are magnitudes. Therefore we can take outside the cross product. Therefore we can write vector FB equal to QVB I cap cross K cap. What is I cap cross K cap? Last year we have studied the cross product of all the unit vectors. I cap cross K cap is minus J cap. Therefore we can write vector FB is equal to minus QVB J cap. That is equation number 2. From this equation, we will get the magnitude and the direction of magnetic force. What is the magnitude of magnetic force? QVB. And what is the direction? Minus J cap. Means negative y direction. Okay. Therefore, the total force, Lorentz force, will be vector F equal to QE J cap electric force plus magnetic force. What is magnetic force? Minus QVB J cap. Taking J cap outside, we can write F Lorentz vector F equal to QE minus QVB J cap. That is, the total force will be along y direction. That is, the direction of electric force is along y direction and that of magnetic force is along negative y direction. Thus, electric and magnetic forces are in opposite directions as shown in figure. Here you can see electric force is along positive y direction and magnetic force is along negative y direction. Suppose both these forces have equal magnitudes. Then what will be the total force, Lorentz force? It will be 0 because they are in opposite direction, and if they are having the same magnitude, they will be cancelled out. Okay. Therefore, in such case, if electric force and magnetic force have equal magnitude, in such case, the charged particle will experience total 0 force. When this happens, when the charged particles experience total 0 force, when electric force and magnetic force both are having same magnitude. What is magnitude of electric force? QE. What is the magnitude of magnetic force? QVB. Therefore, this happens when QE is equal to QVB or V is equal to E by B. Therefore, a charged particle having velocity V is equal to E by B will experience total 0 force only in a closed field. Since the total force is 0, it will move undeflected. It will continue the same motion without affected by the force. Okay, without affected by the electric field or magnetic field. This is how we are selecting a particular velocity particle among a large number of particles in a beam. That is, we adjust the value of E and B to get that particular value of velocity. Therefore, only that particle and particular velocity will move undeflected. All other particles will get deflected in crossed fields, will be affected by Lorentz force because their Lorentz force will not be equal to 0.